Greetings. In this video, we'll talk about a particular example of a group, and it's a group of two tuples which are real values. That means that the entries are taken from the real numbers, and all the elements of this group are something like basically a set. They are all elements A, B, and it's such that A, B are both in the real numbers. So it's the set of these two tuples. And by the way, I want to announce this channel has achieved 300 subscribers. So since today, this channel has, after almost 3 years, achieved 300 subscribers. So it's a special video in that sense. So what we're gonna consider in this video is basically the operation defined as follows. For whatever two tuples, whatever, in other words, two elements from this particular group, we have a new defined two tuple which will result from that, and is defined as follows. When we have these A, B, and C, D here, we will have AD plus BC in the first entry of the new two tuple and BD in the second entry. So what I want to do is to check if we can find an inverse element or an identity element and so on that will suffice for this group. So first of all, I would start with basically changing the notation a bit. This is used in textbooks, but it's probably more practical to leave out this sign of operation. I'll just leave out there a space, so it's basically nothing here. And by this multiplication of any sign, I mean that it's an operation between two elements of the group. All right, so the operation is defined as follows. And if I want to look for the identity element, then I will take some two tuples, some generate two tuples from this group, and I want to put in an operation with some identity that will again have two entries. It will be again a two tuple, and the result of this identity operation, or an operation of a particular any generic element from this group with the two tuple AB in operation with the identity E1, E2 should again equal to the same element. So the definition of an identity is basically does not interfere and it leaves an element of the group the same as it was before. So now we can use and apply to this two tuple this exact definition. So ABBC was ABCD was like this, and so ABB plus BC in this case will mean namely A times E2 plus B times E1, and that will be the first entry of this two tuple, and the second one should be BD, which here meant BD, but here it will mean B times E2. So B times E2, and this should still be equal to 2AB. Now from this two tuple, what I can do is take these individual two entries and compare them. So this first one and this first one, I have A E2 plus B E1, and it should equal to A. So that's one equation I have, and then for the second side here, I have basically B equals B times E2. Now I can cancel out B on both sides, and I get 1 equals E2. This is just arithmetic. Here we're not really talking about elements of the group, because here is defined via arithmetic, addition, multiplication. This is all meant in classical arithmetic. So now we've determined that E2, the second entry of the two entry identity tuple, is 1, and I can put it in this other equation. I yield A times 1 plus B times E1 equals A. So this leaves me with this possibility to cancel out the A's on both sides, and then divide the 0 on the right side by B, which still remains as 0. So E1 is 0. That means that the identity E1, E2 for this group will actually be equal to 0 and 1. Now, we could also verify if this works the other way around, if it actually is commutative, because an identity for a group has to be commutative. If we take some arbitrary element from a group and we want to put in operation with the identity, then A times the identity must be the same as identity times A from the group, where A is some element from the group and an identity, of course, also belongs to the group. But in any case, I won't do it now because of time reasons and practicality, and instead we can straight away start focusing also on the inverse. So because we yielded the identity and we know that the identity should be equal to the tuple 0, 1, now we can actually look for the inverse. The inverse should be some element A prime B prime, which, yeah, it always should be some element A to the minus 1 power inside the group G, such that any element A from G, which I've not mentioned, but I mentioned it verbally here, is commutative with it in the way that it all equals in operation with that element whose inverse it is. It should give the identity that way. So with this case, what we want to look for is a two-tuple that will consist of some, let's say, A prime and B prime, which will be the two components of that inverse to AB two-tuple. And when we put an operation of an element with its inverse together, it should yield the identity. We had found out that the identity is 0, 1. Therefore, we're looking for, again, some equations here. The equations will again be taken from this. AD plus BC is the first element, is the first entry here. So AD plus BC, what will that be? Well, here it will be A times B prime plus BC will be B times A prime. So that will be the first element, the first entry of this two-tuple. Then the second one will basically be, should be BD, which is B times B prime in this case. B prime at the B's place. So we've got this, and it's equal to the identity. So again, some element, arbitrary element from G and its inverse together should give the identity of the group. And this makes sense. This makes sense in the way that we can actually, again, break this out into equations and create this equation as well as we can create this equation. So at the first place, what this brings to us is the quite useful result B prime equals 1 over B. So explicitly, in respect to the elements or in respect to the entries of the arbitrary element of G, we actually got the inverse or one part of the inverse. We can apply this B prime here and just plug it in. So we have A over B plus B A prime equals 0. And now what I just want to do is, again, modify this equation. I can basically do A prime equals minus A over B and divide it by further B, which will make this B squared. So A over B squared minus A over B squared will be A prime. That means that we actually also yielded our inverse element, which is denoted A prime, B prime. And I just plug in here the results we got. So A prime is minus A over B squared, and the other one, the B prime, was 1 over B. If yeah, that's correct from here. So that works. And why this was useful is because we've now, first of all, we've expressed the inverse for any element in G as well. We expressed the universal identity for G, and we can also check for commutativity. If two elements, if they're applied in the other way, they still hold. I've checked this. I'm not going to do it in this video, but you can check it for yourself. And this was a showcase of how you can do it for one side. Then you can switch the idea. So what you can write out is also this times this to the right side. Just switch these two things, and then again it should hold, and your result here should be the same. So what we found out is, first of all, the inverse element for G, it's universal, and then we also found out the identity element, which is this one. Now, what we know is it won't hold for B equaling 0. We would have 0 here in the denominator. So we have to be careful about this. Otherwise, this should work in general. So we basically talked about this group of two tuples, and we've looked at the option to find out the identity for it, as well as to find out an inverse to any arbitrary element inside it.